All right, in this section we're going to be looking at properties of exponential functions. Here's our learning targets for this lesson. I can graph an exponential function by using transformations on a parent function, and then I can write and solve an exponential decay word problem. So let's start by looking again at our graphs. So suppose we have this function, right? And again we're talking our parent functions. B, which is kind of our base, to the x. This is the parent of our exponential functions. So I can have a different factor in front, a different number, which is my a value, and this, just remember, like our other functions, stretches or shrinks and can reflect our parent function. So here we're going to be graphing this function and seeing that this a value is going to be between 0 and 1. So here I have two different examples where a is a positive 1/2 and a is a negative 1/2, and then I'm asked to label the asymptotes. So first thing I always do is I make a table of values, right? So I just write out both of my functions that I'm going to be looking at. I pick some values for x. Remember, we always like 0 and then a couple on the other side of left side of 0 and a couple on the right side of 0. Just makes things easier. And then I just plug those values in anywhere I see an x, and I solve using a calculator or the math, and I get these points, right? All the way around. So then I can go ahead and graph these points. So what I see here, this paint graph, is this first function, 1/2 times 2 to the x. And I see that when I put those points in, I have my curve going up, right? Because we talked about in our last section that if my base is greater than 1, it's an increase, right? It's a growth. So we see growth here. And that my y-intercept is that a value. So in this example, it's that 1/2. We see that my asymptote has not changed, it hasn't moved, it's still the x-axis, so it's y equals 0. So then I look at my second equation with the negative 1/2, and I see that it just reflects it across the x-axis. Now this is similar to what we saw in our other families of functions when we were looking at radical functions as well. It just flipped it across the x-axis. This also tells me that the y-intercept is that a value, or in this case it's that negative 1/2 here. So what I can say is that this 1/2 shrinks, right, because it's less than 1, my function by a factor of 1/2. And if I'm looking at my second function here, this negative 1/2, it reflects it across the x-axis, and it also shrinks by this factor of 1/2. So it just kind of does double duty then. So we can also look at horizontal shifts, right? We talked horizontal shifts back and forth, and again, this looks very similar to our radical functions, x minus h, and this is up in the exponent. So my horizontal shift is the same as a vertical stretch or shrink this way, right, using this. We won't look at this very often. But then I also see that I have a vertical shift, right? My k value, which is outside, it's not in with the x, but it's outside, also moves my horizontal asymptote, right? So here my horizontal asymptote was the x-axis, or y equals 0, because I didn't have a k value. But whenever I have a k value, that will change where my asymptote is. Okay, so here's the second example. I'm using this parent function and I'm going to be translating it. Okay, so I'm asked to graph the stretch, and I know it's a stretch because I have an a value here, and then a translation. So first thing, I graph my parent function, which is in the pink graph, right? So I find some values for x, and I plug them into my equation, and I come up with some y values, and then I plug those points in, and I just graph them. So my horizontal asymptote, right, because I don't have a k value in this example, is the x-axis. So then once I have my parent function graphed, then I can go ahead and use my translations. And I know that this translation up with my exponent, right, goes horizontally. And I have to remember this silly rule, right? I first have to make this a subtraction, so it would be x minus something, and that something is a negative 2, right? So these two, x plus 2 is the same thing as x minus a negative 2. So this tells me that my h value is a negative 2, so it moves to the left. And my k value is 3, and that tells me that it's going to move up. So then I just take the points that I'm given on my graph, and I shift them, I translate them to where they need to go now. And so now you'll see in my blue graph, I have my new and final graph. I also see that my horizontal asymptote has changed from y equals 0 to y equals 3, and that 3 was just my k value right there. So now here you're given a parent function and then asked about these translations. So what I want you to do now is just, you don't have to graph them, but I want you to explain to me what each letter happens. So for an example, I will do part A for you and then you can do parts B and C. So I know that once I graph my parent function, this +1 in the exponent tells me that my function will move to the right. Am I right there? No, because when I have x, I have to have minus, and this is going to be a -1, so it's moving to the left 1. So now go ahead and figure out what B and C, and just explain using words what each of these translations do. Alright, now we're going to move on to example 3, our real-world connection. So I know that the half-life of a radioactive substance is the time that it takes for half of the material to decay. So a hospital here prepares a 100 milligram supply of this magical radioactive material, which has a half-life of 6 hours. I'm told to make a table showing the amount that's left after each interval for 36 hours. Then write an exponential function and figure out how much remains after 75 hours. So first thing I do is I go ahead and I fill out my table, right? So my number of intervals is at the top, and then the number of hours elapsed. So I know if I go one interval, 6 hours has elapsed. My next interval, 6 more hours have elapsed. And then I look at my material, and it cuts in half every single time. Okay, so my decay factor is 1/2. Those are the things I need to know, right? Because it goes in half, and then 1 half-life equals 6 hours. So we're going to write my function. So y equals the amount that's going to be left. So x is going to be the number of hours elapsed. So here I have to turn this into kind of a fraction, right? So 1/6x is the number of half-lives that we've had. So I can write my function. My y equals 100. Here's what I started with, right? The amount that I started with, my decay factor, and then the time that it takes. Okay, so once I do that, that's my equation. That's my function rule. So then I'm asked how much is left after 75 hours. So all I do is I put 75 in where x was, and I multiply here, and then I simplify. So I do 1/2, and to the exponent, 12.5, and then multiply that times 100. So after 75 hours, that much remains, which is really not a whole lot. But you'll see that when we're talking exponential functions, things grow and shrink very quickly. So now using what you just did on that previous example, here's an example that I want you to work on. Arsenic 74 is used to locate brain tumors. It has a half-life of 17.5 days. Write an exponential decay function for a 90 milligram sample. Use the function to find the amount remaining after 6 days. Right? So again, do what we just did on that last example, is first come up with your little table, and then write your function, and then figure out how much is left after 6 days. So here's our big summary from what we've been looking at, especially graphing our parent functions. So my parent function is y equals b to the x. And then I can add another value up front here, this a value, and I know that if the absolute value of a is greater than 1, I stretch my function. If that absolute value is between 0 and 1, I shrink my function. And if a is negative number, then it reflects. I can also have my horizontal translations and my vertical translations. So we can just have all of these different things with our exponential functions. So this table would be something great to write in your notes because you'll refer back to it a bunch. So now we have just our different homework. These are also listed in your calendar, so check there before you get going and stuff. And then let's just go double check our learning targets. So here they were. I can graph an exponential function by using transformations on a parent function. Now this learning target, that table on the last slide is going to be really helpful for this. And then I can write and solve an exponential and decay word problem. So you're going to be doing some of these things, graphing in your homework. Don't forget that when you are graphing in your homework on your paper, you must use graph paper, which if you don't have some, just swing by my classroom and pick some up. But we want to have very accurate and mathematically correct graphs, so we do need to use that graph paper.